Welcome to the last video for the integration topic. We're going to be looking at sums and differences of areas. Now, there's not really any theory that we need to cover. We're just going to use the skills that we've developed throughout this topic to help us with some more complex problems. So we've got two examples waiting for us. Let's get into the first one. Number one. Find the area enclosed between the curves y equals x squared, y equals x minus 4 all squared, and the x-axes. So you can see here no lines have been given, but rather two curves. Alright, like always, let's draw a sketch to see what's happening. Y equals x squared is easy enough, but what about the second parabola? Well, remember that when we have x plus or minus some value, and that's all squared, that corresponds to a horizontal translation. So we want to move our standard parabola 4 spots, and in what direction? Well, the minus, it's counterintuitive, but it means to the right. So we want our vertex to now be at x equals 4. And so once we sketch our second parabola, we can now see the area that is enclosed between them and the x-axis. But because this area lies underneath two separate functions, we need to split it down the middle and focus on one part at a time. However, what is this x value? The x value of the point of intersection. Well, we know this vertex lies at 0 and this vertex lies at 4, and because they are identical parabolas in shape, we can use symmetry to see that this must be 2. However, you could set x squared equal to x minus 4 all squared and solve if you wanted. Or you could just, once you have your guess of 2, substitute 2 in to both equations and check you get the same answer. So 2 squared is 4, and 2 minus 4 all squared, well, that's negative 2 squared, which is also 4. So good, we have got the correct x value. And so now on to our two areas, area 1 and area 2. Our total area is going to be the sum of these two individual areas. Area 1 lies between 0 and 2 and is underneath the y equals x squared parabola. Area 2 lies between 2 and 4 and is underneath the x minus 4 squared parabola. But by symmetry, you might notice that area 1 is just going to be equal to area 2. And so if you wanted, you could find the total area by just doing 2 lots of area 1. For this example, we will do both integrals and just check that they are the same, but that is one potential way that would be a little bit quicker to solve this. Okay, let's start by finding area 1. So like I said, we are going from 0 to 2, and we are underneath the x squared parabola. Integrating x squared, we get x cubed on 3, and then evaluating for the values 2 and 0, well, 2 cubed, that's 8. And 0 cubed, well, that's just 0. So there we go. Area 1 is 8/3. What about area 2? Well, for this integral, we are going from 2 to 4, and we are underneath the other parabola. Integrating this using the chain rule, I suppose, we've got x minus 4 cubed over 3. But this is an easy chain rule because the inner brackets here, the x minus 4, the derivative is just 1. So we actually don't need to do anything further. We can leave it like that. Remember, if you're ever unsure, just derive your answer and it should take you back to the original integral. Okay, once again evaluating. Well, when we sub in x equals 4, we're just going to get 0, aren't we? Because 4 minus 4 is 0. Takeaway, what do we get when we sub in x equals 2? Well, we are going to get 2 minus 4, which is negative 2, cubed, which is negative 8. And so when we look at 0 take away negative 8/3, the two negatives make a positive, and we just get 8/3. So just confirming then that the second area is exactly the same as the first area. That means our total area is area 1 plus area 2, which is 16/3, or 5 1/3, if you wanted to express it that way. Okay, on to example 2. Find the area enclosed between the curve y equals x squared and the line y equals x plus 2. Notice in this question there is no mention of an x-axis or a y-axis or any lines. And so we can guess that the area is going to be completely bounded between these two functions. Okay, let's start with a graph. And y equals x squared we'll do first again. And then the line, well, that has a y-intercept of 2 and a gradient of 1. Now that we have our sketch, we can see the area that is enclosed between these two functions. But how do we calculate it? Well, once again, the points of intersection, just like in example 1, the points of intersection are going to be helpful here. But this one's not as clear cut. See, we could use symmetry to help us in the first example, whereas for this one we might have to set these equal to each other. If you want, you could do a little bit of trial and error to figure them out. But let's go ahead and solve these. So y equals x squared, but y also equals x plus 2, meaning they're equal to each other. This is a quadratic, so if we move everything to the left-hand side and have our right-hand side equal to 0, we can factorize and solve our quadratic. Factorizing this, what do we get? Well, we get x plus 1 and x minus 2, meaning that the x values are negative 1 and 2. So let's add them in over here. But what do we do now? Well, notice that we have this entire area underneath our straight line. Let's call this area 1. Now, whether we use an actual trapezium, which we could do, or whether we use the integral of x plus 2, so the area under x plus 2, either way is fine. When we go and solve this problem, we will use the area under the curve, so the integral of x plus 2. So in order to find the area that we are after, A, we can take area 1, which was the green area, and subtract the area that is underneath the parabola, which is this area here. So let's start with area 1, which is the integral from -1 to 2, the function x plus 2. Then we'll focus on area 2. which is the integral also between -1 and 2, but it's the area under x squared. And so while we could go and evaluate these individually, something cool happens when we have the same limits. We can simply combine these into the one integral. So between -1 and 2, we can look at the function x plus 2 minus x squared. See, in this entire domain, the x plus 2 line is always above the parabola x squared. And so evaluating it as one single integral is going to be a bit nicer. So the integral of x is x squared on 2. The integral of 2 is 2x. And the integral of negative x squared is negative x cubed on 3. Evaluating this for 2 and -1, let's see what we get. First, plugging in x equals 2, we get 2 squared on 2, so that's just 4 divided by 2, which is 2, plus 2 lots of 2, that's 4, minus 2 cubed on 3, that's 8/3. Now we have to substitute in -1, so we get -1 squared, which is 1 over 2, plus 2 lots of -1, so that's -2, minus, well, -1 cubed is -1, so the two negatives make a positive, and so we get 1/3. Adding and subtracting all of these terms, we get our final answer of 4.5. And since this is an area, that's 4.5 square units. Okay, excellent job. Well done in this video, and well done on making it through the integration topic.